you don't mind doing an introduction about how was DDexec, DDsc, and well, Tailexec and the other brands of your exec stuff, how they were created?
Well, it all started with a question that you made me. In fact, in January of this year, you asked me how to load binaries in Linux filelessly, because in Windows it seems, because I don't know how, but it seems it is really easy to do. But in Linux, there are some techniques, or there were some techniques, but they weren't um, broadly documented, and they weren't as complete, because in the end you needed um, a way to execute binary code, native code, um, which is exactly what you intend to do when you run a binary. So that was the problem with these techniques. These techniques that used memfd or ptrace or something like that. Those are syscalls, and you can only perform a syscall through a binary interface. That's why it is important to find. It was important to find a way to execute native code, binary code. So when you asked me this, it was because you were in a system that you didn't have any way to run a binary. The file system was read only, I
Read
think.
only and no exec?
And yes, and the few places that were writable, they were with the flag, they were mounted with the flag no exec. So there wasn't any way to place a binary and run it. So I started to think about hijacking a process through the mem file, which is located in the slash proc directory. Um, this In this mem file, you have a map, or it is a one-to-one mapping of the virtual space of the process. So if you write in the offset x in this file, you will be writing, or you will be reading from, you will be writing especially to this address, to the address x. And that's why if you try to do a cut on this file, you will get an input output error,
We are,
because
we are,
you're trying to read from the address 0.
we are talking about the file in a process which is slash proc slash self slash mem, right? If we try
Yes,
to cut it, you are going to have an error because you are reading the memory, but you can actually read or write in there. That's where the
yes,
beauty of this technique is based off, right?
yes. So um, if you only do a cut, you're going to get this error, because you're trying to read from the cut, opens the file and tries to read from the offset 0. So you're trying to read the address 0 of this process. And this address, at least in Linux, at least since some version of Linux, this address is never mapped. You can't map the address, the null address. So you will never find a process that will have this address mapped to something that exists, and you will have an input output error. Uh, but if you find a way to seek through this file and place the pointer um, at an offset where there is something, you can read or write in any place of the memory of this process, and thus hijack it, make it do whatever you want, as if you were exploiting it, but easier, because it is your process.
Okay, so what we are going to be doing here is we are going to find some specific address in the memory that is interesting for us. We are going to be writing on it so we can make a process execute anything. Until this technique, as you have explained before, there were some people doing it, but they will need things like, well, ptrace via GDB or other special tools. However, with this DDexec and other exec stuff, we are going to be able to do this with common binaries without needing to call, well, syscalls that could be not allowed by secom, for example, in Docker. So we are going to be able to use this technique easily in restricted environments.
Yes, because it only uses well, syscalls that are commonly used, like open and seek and mmap. These syscalls, you can't restrict them because then you can't run anything. So that's the beauty of this technique. This
There is a question. Do you need skills in assembly language to use this
well,
technique?
yes. To to use the technique, no, you don't need the knowledge because I have created this tool. So this tool is automatic. Um, but if you want to research in this area, yes, you definitely need assembly language. Um, x86 or ARM, they are both very important right now. Well, x86, the 64-bit version, also called AMD 64 or x64, and ARM 64, also known as AR64. I don't know why they give so many names to these architectures or these ISAs, but well,
Cool. So it is definitely important. So okay. So how could you use in this case Didi to well how could you find the memory place where you want to write, and how will you write with Didi, and how will you execute that well the thing that you just wrote in memory?
um, well, the idea is about using the information that the kernel provides about a process in the procfs file system, which is usually mounted in the slash proc directory. This interface is used normally by debuggers, and I don't really understand why they are enabled by default in well every system I have seen. Uh, if 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 it depended on me, I would start to disable these features by default. Unless you wanted to be a developer, you don't need these tools or these interfaces. Well, so in the slash proc slash the pid of the process slash whatever, there are a lot of files and directories that contain other files. All of this is a lot of information about the current state of the process. There is one file which is called syscal. This file contains information about all the information related to the syscal that the process is currently doing. So if you look for a syscal for the in the syscal file of a shell, for example, you will find it a lot doing the syscal read because it is expecting input from the user. Now, we can use this information because it contains, I said that it contains all the information related to the syscall. It contains really all the information. It contains the syscall number, contains the 6 parameters it may have, contains also the stack pointer it had when the syscall was performed, and the return address, which is the one parameter that is more interesting for us, because with that return address we can know the position of the library in the address space of the process. And this is vital because systems nowadays have ASLR, so the position of any loaded object is partially random, and it is really difficult to predict where it is loaded. So this is a way to know where the library is loaded. And we also have the maps file, which can also give us a lot of information. The syscall file is interesting for another bit, which is where the program lives normally, because we will want to overwrite the code that the program will more promptly execute, because we want if we overwrite some code that will never be executed, we won't be doing anything. So we want to overwrite code that will be executed and as fast as possible, because many things can happen to a process. And if we overwrite a code that was executed a minute ago, and it will be executed in another minute, the process may die in the first before it can get to execute that. So we want to find some place that will be that the process will return to fast. And syscall for certain kind of processes like shells is particularly useful for this.
So, as a summary for the people that just joined, what we are discussing here is that we are going to be writing inside the proc self mem file in order to write our shellcode there that will be somehow executed. And Yago just said that in order to find the place where our shellcode is going to be executed, we have some files that can give. There is a file in the proc environment that will give us the return address of the current syscall. That if we overwrite that, we know that the pointer is going to get there at some point if we are lucky, and in the tools that Yago is going to show, we are going to be lucky, and our shellcode is going to be executed in memory.
Yes, exactly. Well, it isn't about luck, because we know that the shellcode will be there, that the process will execute the shellcode. It is luck, but 100% luck. So the technique before when I thought it used it was slightly different, but I came to know that another person, which is another researcher, really famous, which is called David Buchanan or Buchanan, I don't know. I should check that. He developed a slightly better technique a year before I even started to think about the technique. His technique.
Do you have the tweet in there? Would you like to share your screen and explain it with with that in place?
The tweet, yes, I have the tweet. I have it here.
If you don't mind
Um,
sharing your screen.
okay.
Someone asked, is this the operating principle of rootkit? No, the answer is no. We are not touching
No.
kernel in any way. We are just living in userland.
Yes, we are modifying the behavior of another process, not modifying the behavior of the kernel.
Can you make it a little
So
bit bigger? Awesome.
like that.
Yeah, perfect.
So here we have the tweet. This well, this script, well, it works, but I think this one what did was to shut off my computer, so I'm not gonna execute it right now. Uh, um, this is a very golfed, like he says here, version. So I think he started to play with golfing it, but here we can see it more clearly. Here, what he's doing is well, running DD to seek through this mem file because of what I said earlier that seeking is vital. It is writing to the mem file of the shell that is executing this command, 1 byte at a time. This is important because it also defines the size of the seek. If you put here 512 bytes, this inside the seek will be interpreted in blocks of 512 bytes. So that's why this is important. So he seeks to well, the value that is contained in this file. We can we can see here. Well, we can see here an example of a syscall file. Here we have the syscall number.
Can you do it bigger?
Okay. We are seeing here. This is the syscall file of cat because I placed here self, and cat is opening this file. Self is always pointing to the
current
proc
process.
directory of the process that is referring to it. So 0 is the syscall number of the syscall that cat is executing right now. As cat, right now not. When this was printed or when this was executed, cat was reading. What was reading? Well, it was reading precisely this file. So this 0, we can check. It is the syscall number for the read syscall. Now we can see here the file descriptor. So cat first opened this file, and the kernel gave it this file descriptor, the file descriptor 3. Then he is telling the kernel that he wants the data written in this address. It wants to read this amount of bytes. Well, these 3 arguments here aren't used in the read syscall, but the kernel shows us them anyway. And here we have the stack address, the stack pointer, and here we have the return address. So it is the 1, 2, 3, 4, 5, 6, 7, 8, 9. It is the 9th field of this file. So what cat is doing here is splitting the string the string obtained from the syscall file, the syscall from the shell. It is reading it and splitting it by spaces and taking the ninth field, and that's how it is obtaining this address where it wants to write, and then reads this shellcode here, which I think this one is I'm most certain that this shellcode was the one that
Yeah,
he
I
shut
said
down
yes.
your machine. Yes.
So
Um.
if I can interrupt you about a question, yeah, I was going
Mhm.
to go there. Does this technique really require root and JAMA
No,
disabled?
no. It requires JAMA because it is reading directly from and writing directly to these files. Um, as we saw earlier, if I try to read this file, I can't. If I disable this protection, no, I can. But it isn't needed because of the smartest thing I have seen in quite a long time. Also, idea of David that we will see in a bit. And no, it doesn't require root. This shellcode requires root because this shellcode is starting to shut off your machine,
Okay.
and only root can shut off the machine.
Another question. I guess if you're root, you could be able to access the proc self, well, the proc
Yes,
mem of other
yes.
processes. Would you be able
Yes.
to pivot to other users and to other processes and, well, use them to perform potentially bad stuff with this technique? So the system administrator or the blue team, once they discover like, hey, this Apache is doing weird stuff, they believe that the Apache was compromised, but actually is that you just pivot
Yes,
to that process.
yes. Being root. Yes. And now we are getting really close. Not just to pen testing tools, which is what DDexec is about, but to malware. Yes, you can pivot to other processes and make them create a thread, and in that thread run your code as if it were an independent program, uh, or use more hidden techniques,
Awesome.
because a thread is still a bit noisy.
Well, maybe in a different Twitch, you can let us know other techniques to use this more stealth. Would you like to do a demo about how to load with this technique a shellcode?
Okay, so let's see. I have I have in GitHub an example. Yes. So here I have this shellcode, which, well, we can disassemble it. Mm, this shellcode, what does is, well, first pushes a string in the stack. This string will be used as a name for the memfd, and then, well, prepare some parameters for the syscall, and then makes the memfd create the syscall to create, well, a memfd, a mem file descriptor. It is memfd create, just for the curious. um, it is a syscall that lets you to create a file in memory, and the kernel will return you a file descriptor to it. And that's why it was so used when doing, while trying to run filelessly binaries, because you can create a binary in memory, and then you can you can do something like the syscal exec. Well, this yes, the syscal exec ve at, which receives a file descriptor. So you have a file descriptor to a file, which is a binary file, and then you have this syscal that accepts a file descriptor, do the math. That's why it was it was used. But we have this problem that you need to execute this, and you only can execute this if you can run a binary that has this code. So well, we have this memfd, and then I think this what this did was to truncate the file. Well, we can see 4D. For the f truncate, and because you need to give the file like a size, and then 22. Nope. Pause. Okay, because I don't want the process to die, so I just pause it. Pause is a syscall that well makes the process wait until it receives a signal. So that's the shellcode that we are going to run. We can even run it using well using the tweet from David, just to honor him.
Okay, so we are going to be running a shellcode that is going to create a file in memory using memfd that will allow us to write a real binary in this file in memory and execute it. So we will be executing something without touching the disk and without needing to execute a special binary to load it, because we are just running DD.
Yes.
Okay.
So here here we have DD, which is receiving from a pipe in the standard input, is receiving the output from this xxd, which is reversing the hex encoding of the shellcode. And here DD, we are using it only to well to seek and to write. Yes. And here we have also the processing of well, we have the a variable here, which is going to hold the information from the syscal file. This command is very golfed. If we go to any /proc/pid directory and do an ls, we can see that there is only one file that has that ends in L, and that's why this is working.
Okay.
It is using wildcard expansion here to read into the a variable the contents of the syscal file.
User joined your channel.
And oops. So I think I have done everything correctly. So okay, this is good, and we should have, yes, I think the PID we are interested on will be the second one. And in FD, we will find, yes, we have here this memory file descriptor.
That's
And now,
the file in memory that we have generated with that shellcode.
yes, this file descriptor was created by the memfd code. In fact, I can repeat it and show you. Well, I'm gonna copy this command because I don't want to lose it. So we have this bash, and we can go 16.64.0, and we can go see its file descriptors. It only has these four. I don't know why bash uses the 255 descriptor to hold the file with the input it has. If you are running like a script and you see the file descriptors that the shell that is executing this script has, this file descriptor will be pointing to the script. I don't know how bash uses it internally, but I don't know. It seems kind of funny to me. Okay. Anyway, back to the business. So
yeah, let's run this.
yes, we execute this. The process is paused, and now we can see here. Well, we have this file descriptor. Okay. I forgot to explain this.
Yago,
This
we
is
are,
why we don't.
Yago, Zoom is going to end soon, so let's restart the session, okay?
Oh, okay.
Cool.
This is really sad.
Yeah. See you in a second. Sorry, guys, but we will get back in a second. If any of you have any question about how is Yago loading binaries and shellcodes in memory, leave them in the chat. I have left the URL for his free project DDexec from GitHub in there, so you can use it also. Let's see if Yago connects.
Hi.
Okay. Hey Ben, let's continue.
Oh, you're back. Okay. I forgot. Oh, I have to share the screen again. So I forgot to explain why we don't need to be root like it says here. What has changed from this command to this one? What has changed is that we are exploiting a really beautiful thing in Linux that I think also exists in Windows, which is I think in Windows it is called leaked handlers or leaking handlers. So we are making the shell create a file descriptor pointing, well, a file descriptor with writing permissions pointing to its own main file. since the process does have access to its own main file, like we saw before we saw that I can't access the shell's file syscall from cat, because cat and the shell are different processes. So I am going to get an access denied. I have the shell in Spanish. But when a process tries to access its own files in this directory, it can, and the same goes for the main file. So it is a POSIX standard, I think, that you can create a file descriptor pointing to a file with only writing permissions or only reading permissions or reading and writing permissions to a file. And well, I'm not sure if I want to show you that file. I don't know. I don't know if I have some file here. Okay, with reading permissions, and now I can read from it. So I think it is a POSIX standard to create in the shell file descriptors that you can choose which file descriptor you want, and this file descriptor will be inherited by by subsequent processes executed from the shell.
So basically, what we don't need to be root because we are going to be creating a file descriptor to the original program mem file. So the child, which is
from the we are going to make, since the program we are trying to override or exploit is a shell,
yeah,
and thus we have a lot of control in what we want it to do. We have this way to tell the shell, to tell bash, to create a file descriptor. In this case, we wanted the file descriptor 3 with writing permissions to its own mem file. And this file descriptor is going to be inherited by any other process. It will be inherited by XSD, but XSD isn't using it anywhere. And it is going to be inherited by DD. And DD is going to be using it.
cool. So that's the way we allow DD to write in the memory of bash to execute something.
Mm-hmm. Yes. So because only the process that owns the mem file can create the file descriptor. Well, only the process and root can open a file descriptor to it, and that's the beauty of it.
Awesome.
So now we managed to run this shellcode, and this shellcode has performed the syscalls that I showed earlier, and created this file descriptor. So now we can just redirect something to this place. No.
I think it was
4
5,
no,
yeah.
5, yes, and we can run it as if it were ls, and well, we can just I don't know, just to make. Oh, I have something here. Okay. I'm gonna use this. Just, I don't know, to prove a point. We can get this listening here, and well, I may even do something like it was like this, I remember. Oh my god.
Yeah.
No. How was it?
No, I think the path is correct. Are you in a bash cell or in a
This,
different?
yes. This is bash, yes. But I think yes. Maybe okay. I think this way this will work. Okay. Well, This is because T echoes what is writing to the file. I should have used which option was? Oh well, I don't know. And well, the fact is that now we have here this file, this program,
So
and we
what you have done here, because it has been a little bit fast, is you have compiled a program that is going to say hello world. You have exposed it in the network, and then you have loaded it inside the file in memory we have created, loading the shellcode with DD, and have executed that file. So actually, the binary you compiled didn't need to touch the disk because it was loaded in this
no,
memfd file.
this file didn't touch the disk at any point, and it has been run.
Cool.
Yes, and as you can see, this technique using memfd is also very um, flexible. I'm not sure that that's the word. You can you can execute as many programs as you want, as many times as you want, as long as this process doesn't die out. And well, it shouldn't die out ever. So that's the beauty about memfd.
Cool.
Um,
I'm gonna be honest with you, Jago. I know this was one third of what we wanted to discuss today, but we have consumed probably more time that needed.
okay.
Yeah, probably stop sharing the screen if you're going to put me.
Yes.
um, do you want to talk very briefly about your technique to load binaries in memory without using memfd, because using memfd is very noisy? So then we have enough time to talk about Tailexec and how to avoid EDRs. Would you like just to explain how your technique about loading binaries and do the demo maybe in 5 minutes, so we have enough time to talk about new
Yes.
techniques?
Yes. So I'm gonna share screen again.
Yep.
So I created the DDexec, which is this small script you are seeing here. This script, what does is receives from the standard input. Let me find it if I can. Okay, here it reads in this binary the file that you want to run, and well, it just processes it. It uses let me drink some water. It uses functions like this one. This one is probably the most important function in the script, because this creates the shellcode that is going to to be creating the memory mappings, in which it is going to read the binary. A binary has like some plans of how it has to be loaded into memory, of which parts of the binary need to be loaded. And well, we can see them here using readelf. So here we have what are called the program headers, and in the program headers, the ones that are of load type are the ones that tell the kernel, in fact, about which chunks of the file need to be loaded. So we have the offset and the address, the size in disk, and the size in memory, and this is what DDexec is doing, is just looping through all of the program headers, looking for the ones that are of type load. I'm gonna do it greater, larger, and well, obtain these parameters that we have talked about, and well, create the shellcode.
So DDexec is basically a shell script that is going to be reading the headers of the file that of the binary that you want to load and crafting dynamically a shell code that is going to be used with DD to load this binary. Is just crafting this shell code dynamically, just using shell script, right?
Yes,
Wow.
yes. Well, I could use readelf, but the problem is that not every system has readelf available. So that's why I had to go wild.
Yeah, no, I can see that.
Yes. And yes, this function also processes the section headers. Well, there's a lot of ELF processing in this shell script. So what we are going to do is do the steps that the kernel does when when you execute a program. When you do the execve or the execve at syscall, the kernel, what it's doing is reading the file that you provided and doing this exact same processing, and creating these memory mappings, reading the file in in them. I don't know, the same, almost the same steps, because well, I'm trusting the binary. I'm trusting that the binary is not ill made. But the kernel has to check that this address plus this offset doesn't get into kernel address space, which would be a very bad problem. So this is like a kind of simplified kernel or kernel loader. Also, the loader, which is like like a library, but isn't quite a library. And the loader, which we can see it here. This is the loader. It also has these routines, because it has also the duty to load the rest of ELFs that are used in the process. So ls has these dependencies. ls is loaded by the kernel, and the kernel also loads the loader, but it's the loader who is going to load libc and libcap. Well, the VDSO is also loaded by the kernel. Well, not loaded. The VDSO is already loaded. It just maps it, and that's it. So let's see.
Let's see it in
A demo?
action.
Yes. So well, I can do it in the same fashion as the other one. With this program, I am compiling it and exposing it in the net. I am using here TCP, but you can use HTTP if you use curl or wget. But well, I don't know. This is simpler.
So for the people that have just joined, you are exposing a binary that you have compiled that is just going to print hello world. And we are going to be loading that with the technique you just explained us. We are not going to be using memfd anymore to load a binary, but we are using the dynamically created shell code that will mimic the kernel in order to prepare the binary to be loaded in memory.
Mm-hmm. Well, it will be easier if I do this. If I already send it um, encoded in base 64, because DDexec needs the binary encoded in base 64. And we can use the same here. Oh. Okay, I think everything is fine. Okay, it worked
Awesome.
perfectly. Yeah, we can try using something more heavy.
Can I ask you for something? Would you be able
Yes.
to fastly modify a little bit the code of the loader so it also prints the cell code that it is being loaded in memory?
Yes, that's totally easy. Um, I think this is enough. So we can. Do I go for A or for ls?
Whatever you prefer.
Okay, ls. So now I'm going to to be passing to ls this argument. This will be the name that ls is going to be seeing. You can see that it worked perfectly, but I don't know why it didn't print it. So I'm going to. Oh, okay. No, I'm just dumb. I'm Carlos.
You didn't
Exactly
modify
what
the
you
correct
said.
one.
Exactly what you said that would happen has happened. And we can disassemble it. I
Wow.
think I had an alias, a very ugly alias. Okay, this is disassembly of the shellcode.
This is a shell code that was dynamically created by a shell script, by
Yes.
a route, a very, very, very ugly shell script.
Well, this is a shellcode. So we can see here we are preparing for the M maps. We are making a map receives 6 arguments. The fifth of them is the file descriptor. Since we are creating anonymous mappings, we have to put here -1. So we are 0 on the R8, which is going to hold this file descriptor, and then negating it. So that's R8 is equal to -1 right here. These are the flags for map unknown. Well, here. These are for map unknown and map private. Here we have map private and map anonymous, which is the same as map unknown. This is telling the kernel that we want anonymous mapping. That it isn't going to be that we aren't mapping a file into the memory. That we are just requesting for memory. And we also tell the kernel that we don't want this to be shared memory, that we want private memory. So we OR these two constants and we get 32 in X. And we put the 9, which is the syscall number for mmap. Here we tell the kernel where the address that we want this mmap in, and then we perform
This is called.
the syscall itself. And the same, then we read. I think yes, we are reading. are we? Yes, we are reading. This is a read. We are reading the binary into this. So we map to this address, and then we read into this address. We read this amount of bytes from the standard input. So that's it. And then we make the read. We check that we have read this exact amount of bytes. If we haven't, we return here and repeat the read until we have read in total this amount of bytes. Because some things may happen with the pipes and occur what we call a buffer underflow. So we may consume the bytes quicker than the shell is putting them into the pipe. So we need to be sure that we are that we have read all these bytes. And well, the shellcode isn't really too difficult to think of because it doesn't do any processing. All the processing is made in the shell script, which was the hard part to do. The shellcode only does what the shellcode only does are syscalls. Yeah, and that's it. And
Yeah,
here,
well, I mean, pretty impressive. A set of script is generating this. Um, okay, awesome, man. So we have seen how we can use DD to write in a proxel in a mem file, a cell code, and execute it, and even load a complete binary. But this is something we already presented in RootedCon this year. This is something you even told me that there are some EDRs that are aware of this technique and are trying
yes,
to catch it. So as far as I know, these last weeks you discover new ways not only to do this DDexec and DDsc techniques more stealth, but also to do this technique without using DD. You can use other very common binaries. So this will completely destroy EDRs because they are looking for DD.
yes,
Would you like to talk a bit about that?
yes. So returning to the beginning. Well, I don't know what happened here. Uh, returning to the beginning, when we said that what we needed was to seek through the mem file. Uh, that's it. We needed to find a seeker, and by default, the more easy to use was DD, because we can tell DD to just seek here and write from the input to the output. So that's why DD was the first thing that came to mind. And I was also looking for other alternatives. The problem is that any other program that I tried that was able to seek through a file were programs that processed the file, read the file, and print data about the file to the output, to the shell, to the terminal, but they never wrote to the file, and that was a problem. But there is a very interesting piece of information about file descriptors, and specifically inherited file descriptors, because you can create well, as we saw earlier, we can create a file descriptor pointing to a file. So now I can read from this file descriptor. Okay. What is happening here?
No, you need to
yes.
use exec, yeah.
Yes. I'm so stupid. But but I'm not seeing what I'm doing wrong. Well, okay, doesn't matter. We can okay. I don't why. Okay. I overwrote this file. Okay, I don't know when, but
I think it was when you were doing the echo
yes,
instead of
echo.
exec.
Okay. So I'm gonna write this program. So 3 and 0 secure. Okay. So now this this program is going to be telling us the at which offset the the file pointer inside a file is through the file descriptor 3. um, so now that we have no file descriptor, okay, we have, I don't know why, but we don't have file descriptor 3. So the program is outputting -1. If now I create well, I don't know why not. If we create this file descriptor, the file descriptor 3 pointing to the mem file of the of bash, now we can see that we are at offset 0. That's why if we now try to read from this file descriptor, I'm not really sure what's going on here. Okay. It doesn't matter. Okay. If we try to read through this file descriptor right now, which is at offset 0, we should get this error, an input-output error, because we are trying to read from the address 0, which isn't mapped. We have here all the ranges of addresses that are mapped, and we can see that there is no address 0 mapped, and that's why we are getting this error. Now, if we seek to this offset, and I created it. Okay, I created it with. Oh, okay. I understand now.
You didn't create it with read access, right?
Yes, it was with write access. Okay. Okay, so if we see here, and now if we try to read, okay, that's more like it. And now we can use these. We are seeking. So seek, I always forget this. In DD, seek is for the output. Okay, so now we have to redirect the output to this file descriptor. I think, okay, bs equal to 1. And it just stood there for a moment because it was trying to read from the keyboard. I just pressed Control D to input an end of file, and the program ended. So now we can see that the offset in the file descriptor has changed. So the file descriptor is inherited, and broader programs, because all these programs, DD and A and CAT, all of them are brothers, are sons or daughters from the same program. Brother programs may alter the position inside a file through the same file descriptor if they all inherit the same file descriptor. So we can just do so we don't really need DD to write to the file anymore. We just use it to seek through this file. We don't even need to use it to write. If we tell it to skip, which is for input, and we redirect the input from the mem file, we'll see here that we have actually skipped 1,000 more bytes forward. We were at the offset 1,000, and we are now at the offset 2,000. And this works with tail too, because tail reads, and we can tell it to read at a specific offset.
So what we are
Yes.
doing here is we have given child processes read and write access over the bus mem file, and we are using other binaries to move the file pointer inside that file in order to move it until the byte offset we are interested in writing, and then we will write in there, right? So basically, we are simplifying the technique using DD that will need to skip some offset and then write. We are simplifying this technique in two steps. One, where the first one is let's move the file pointer until the moment I need to write, and then I will use other child process to write in there. So we no longer need DD. We can use other binaries like tail, as you are going to be doing now.
Yes. So now we can expect after executing this command, we should expect, and we will see that the A program will tell us that the pointer is now at well, not quite 3,000, because tail is a bit special, but 2,199. So okay, we have an error because we are reading from the offset that I'm saying. Oh. Okay. Maybe. Okay, I think I know. I think I know why. It is because it was created with read permissions. I'm pretty sure. So well, okay. Now we are again at offset 0, and now this should work. This should be working.
I mean, you have it programmed, and later we are going to be doing a demo with tail inside the program, so this definitely should work.
I'm really confused now because, well, DDexec before, when we used DDexec,
Is it possible
we
you
were
are missing a plus before the number?
oh yes, you're right. Oh, this is so obnoxious. Okay, okay. So that's it, and it is 999 because tail isn't zero based; it is one based. So okay. Yes. Thank you very much. You saved me. Yes. So if we put here a 1, okay. And actually, before, when I ran DDexec, we were using tail because it is
Oh.
now by default. Tail is by default the binary that is being used right now. Except if you are in VisiBox or Toybox distributions, I mean distributions that use these binaries as alternatives to um, to these utils, these tools. Why why in these distros? Why we can't use Tail or the other alternatives that I have found? Why can't we use them if they are VisiBox or Toybox? Because the implementation in VisiBox or Toybox is really bad, and for every file, small or large, they they get to the offset that we are telling them to get by using read instead of using lseek,
Okay.
which is really annoying, and I don't know why would they do that, but that's okay.
And I guess that will
So,
that because you are reading the main file that will break the execution.
yes, because it will try to read, not to seek. So yes. Um, so yes, the user can specify a seeker,
Harry Potter
but by default,
vibes.
yes. Do you know something about Harry Potter?
I. Ooh, okay. The meeting has stopped, so we are going to get back in a moment. Just reopen it. Sorry about that. I promise that if this channel makes it, I will be paying Zoom Pro. But for the moment, this is what we have. Let me try to contact Yago. Yeah, this is super annoying. Yeah. Hey man.
Okay, so um,
Okay, before we continue, let's try to wrap this up in about 10 minutes because we are running already
yes,
a little bit late.
so I was saying why this reference to Harry Potter.
Do you want to share your
Uh,
screen?
yes. So because Harry Potter was the seeker of the Gryffindor's team.
Ah.
So I started to use this nomenclature, and then I kind of I don't know, thought of it, and it made me laugh. So I just put it here. So yes, the user can specify which seeker to use. But by default, if it is unspecified, by default we will use tail. But well, here we check that it isn't a link to VisiBox or Toybox. In that case, we will use DD, because at least the DD implementation of VisiBox and Toybox are
Are safe.
you use LSEG, because if you if you try to use DD, which is intended for like disks and partitions and devices with a lot of data, if you try to seek through them using reads, you are going to cry. So
Yeah, actually,
uh,
I don't know why the others will be doing that. It's a very bad idea, and it's super stupid. Like you have LSIG for
no,
doing that.
no,
This
no,
is only purpose.
it doesn't make sense. But I don't know. I'm not the developer. Um, so, in fact, developing another tool, I found that the glibc was doing something wrong, and I tried to I even wrote a patch, but it just is standing there. Someone got interested, and we talk about it, but I don't think they are going to apply it. So I'm a bit tired of trying to correct things in other projects.
Yeah, that's true.
So
Is there any way
well,
I can see that now this DDexec is prepared to be using tail, DDextam, compare? Can we do a demo using compare, for example? I am amazed that we can load cell codes in memory using the CMP binary.
exactly, yes. It was it was also really it looked also really funny to me. So well,
You put a D. You put CMD instead of CMP. Yeah.
oh yes. um and well, I'm going to input it filelessly, um ls, and here
Wow.
you go. um if you don't trust it, I can show you. Um well, nope.
No, no, we don't want that.
Okay.
Maybe remove the last part so we don't get problems.
Hmm.
Yeah. Wow.
That's the command that is being run.
So from the initial DDexec technique, where we use DD to do LSIG and to write, we said that we separate that into process. First, we run a binary that will be doing the LSIG and stop there and don't die and don't mess up. And then we will use something to write the generated cell code in memory. What are we
Yeah,
using? We are using printf,
we are using printf.
which is
It is the own shell who is overwriting. Uh,
um,
Before we had the son killing his father.
um,
Now it is suicide.
okay, that's an interesting analogy. And I guess this improves the technique because now instead of DD we have four binary options and printf is basically everywhere. Do you know any cell
Yeah.
where you cannot find printf?
Yes. Well, printf is a built-in.
Yeah.
In fact, um, it is. It is. Well, in Spanish, this is saying that it is a built-in.
So the first time you showed me this technique, I told you like, man, if we find a built-in that could avoid the use of other binaries such as tail, DD, or CMP, or XDAM, that would be awesome. We didn't find any. Do you
No,
think this is
and
going to be possible?
we even downloaded the bash
Yeah, I know.
source code, and we're looking for all the uses of lseek, trying to look a way, looking for a way to use that. But nah, it wasn't. It was impossible. I don't know. Maybe with ZSH. or I don't know, maybe other shell,
Yeah,
but
something
with
like
Bash at least.
DDsc or BusyBox, you think that maybe they could contain something?
Well, uh, the BusyBox people, I think they don't know LSIC. So maybe in BusyBox no, but in set shell maybe, because además because oh um uh, I lost the word.
Say it in Spanish, maybe I can help.
Además.
Besides, moreover.
Because besides, um it is a very it is a much more developed and modern than Bash. So it wouldn't seem strange, or not too strange at least to me, that if it were possible with C shell, but maybe I don't know.
Okay, well, that's something we can take a
Mhm.
look into, because it would be awesome if we find, even if it is in SH, that is not going to be in restricted environments. It would be awesome to just find a built-in that is able to do this. So I have some final questions, but is there anything else you want to show us? Maybe do another demo or something you are writing there?
Yes, just here we are prepared for tail, DD, XStamp, and CMP. This can also work with XXD,
Can you
and
make
I
it
think
bigger?
the argument. What? Oh, okay.
Yeah.
And I think the arguments are exactly like XStamp, so it will be like this. I'm just uh,
Don't you need to use single quotes or? Oh, okay, yeah,
yes, if yes, I can
yeah.
use single or escape it. Um, so now we are telling DDexec to use XXD. In fact, I'm going to place that line again. Okay. Um, okay.
Wow.
So you can see here that this is the command that is being executed, and well, it
So,
worked. So
so
I'm just showing that if you find another binary that you can use, please tell me. Um, and if it is widely used, I will add it to DD. But since XXD um, isn't in every server or every distro necessarily, that's why I didn't include it. But this example is in the repo, so it is documented there. And every other example I would like to document them. So please tell me if you find anything, and also so you know that you can still use it without the need to modify the script.
this will be like living off the land binaries to load things in memory in Linux. So this started like, whoa man, maybe you can override DD memory and execute things in
Yes.
memory. It's like super high tech, and now it's like, hey man, let's discover more binaries you can use for this.
Yes, it was something like uh, totally unexpected, and now it's like day to day and more. Please, more ways.
Well, you haven't mentioned it, but this is working for both AMD and ARM. This is working also
Yes.
with ARM, which is awesome because you
Yes.
can use it in. We had this question when we presented this technique in RootCon, in RootedCon. Yeah, someone told me like, hey, I have this problem. I have this IoT device which doesn't have almost any capacity on the disk, so I cannot cannot upload a lot of binaries, but it has a lot of memory. So if I could load things in memory, it would be awesome because I could just load everything there and run it. Well, you can also use DDexec to do that.
Yes, and it is the same script. This very same script. I'm just copying and pasting it in oh no, in an ARM64 machine. Oh well, it works.
Awesome.
It works perfectly.
So let's wrap this
With
up,
tail.
man. Or with tail in this case, yeah. Actually,
What?
you left that. So let me ask some final questions. Something that should be very interesting for people. You said that you are specializing in macOS. Well, as you definitely know, a problem with this technique and macOS is that well, macOS doesn't have the /proc directory. Is there any technique we could use to load things in memory in macOS or in systems without the proc directory?
Well, I'm currently not in OS X. I am in iOS. So about OS X, I don't really know much either. But as far as I know, no, there isn't. But maybe a fast Google search can prove me wrong. I don't know.
Maybe we can ask ChatGPT to give us a way to do that.
Oh, that that would be. Can you believe that I haven't tried?
Oh, come on.
No, I haven't tried. It is here.
Yeah, but you will need to sign up.
Oh, okay. Well,
Chat.
I don't know. just to try something. Hmm. Oh, fileless. Oh, it seems that there is a fileless technique. Well,
Okay,
no, but it is no. They are placing just a binary somewhere.
but that's not fileless.
No, no, but I think mm,
Well,
so. I'm guessing that if you infect a process, well, in OS X, there must be also a loader, and you can, or even you can, exploiting a binary, you can write a shellcode. So you may do the same that we are doing here. In any system, also in Linux, by pawning a binary, you can make it execute some shellcode, and that shellcode maybe uh, one created with this tool even, and thus load a binary
so
without touching the disk. But and yes, you aren't using the mem file or any data from the /proc, but well, you need to find a vulnerable program. But if you find a program that you can exploit, even if it isn't a program suitable for privilege escalation because it isn't set UID or something like that. It doesn't matter because you only want to execute it because it is the only thing that you can execute, and then pawn it just to make it run what you want. So that will be a way. So what I'm reading here is that this is what they are doing, I think. I don't know.
Yeah, maybe we take a deeper look. So I have asked ChatGPT about how to do this, and its response was, yeah, of course you can do it. You can run echo hello world in sh and it will execute filelessly. And the next response was, if you want to execute filelessly a binary, you can also do sh path to binary file. Well, maybe ChatGPT is not perfect.
Yes.
Okay, well, Yago, it was a real pleasure to chat with you. These techniques are awesome. I think there will be more, even more coming. I know there will be even more coming. And maybe in 2023 we can take a look about how to do this in macOS, in iOS, and improve even
Yeah.
more this technique. So thank you very much to have this talk, to dedicate us this time. It's awesome what you are doing. I think until these techniques, well, yes, David Buchanan shared the technique, but not a lot of people were actively using it. I think that is going to change because this is far more easy to use. You just need to use this script. And well, thank you, man.